remember, we're talking about linear independence, this sort of amorphous notion that hopefully will become clearer and clearer as time goes on. And we finished up with the observation that linear independence is equivalent to the linear independence of a set E1 through Dn is equivalent to the fact that none of the Vi is a linear combination of the others. That's basically where we stopped. Okay. Okay. And we, I think we stated this, but we did not get to thinking about it, that if there's another way of characterizing linear independence, if you have a bunch of vectors in a vector space, turns out that they are linearly independent. If and only if everybody in the span can be written uniquely as a linear combination of the Vi. Okay. Everybody in the span has a unique is uniquely expressible as a combination of Vi. Okay, and that's that will basically give us our coordinate system. Okay. So you'll have some set, and you have a linearly independent set inside that set. You have some, you have some vector space, and then you have inside the vector space you have a linearly independent set that spans that space. Well, this theorem will say that if you pick anybody in that space, well, it can be written uniquely as a linear combination, right? In other words, there's a unique set of coefficients that you can use to obtain that, to get that vector. So that unique set of coefficients are going to be your coordinates. I'll say it again. Okay. So the way this is going to be useful is as follows. You have some vector space, and then inside the vector space you have a linearly independent set that spans the whole space. Okay. Then, for anybody in the space, this theorem says there's a unique way of expressing that guy as a combination. Right? So anybody in the space, there'll be a unique linear combination that yields that guy. Well, use the coefficients from that unique linear combination as your coordinate system. Okay. That's what we'll use. Anyway, we'll get to that soon enough. Okay, so let's try and prove it. Okay. So let's go backwards first. The backwards direction is actually easier. Okay. So suppose you know that everybody in the span can be written uniquely as a linear combination of the Vi. Okay. Suppose you have this property. Everybody in the span can be written as a linear combination of the Vi. And you want to show that the Vi are linearly independent. So why does that follow? Right? You want to show that the Vi are linearly independent. So you have this fact. You're given that everyone in the span has a unique expression as a linear combination of the Vi. Right? And you're trying to get to the fact that the Vi are linearly independent. Right? Trying to get to the fact that the Vi are linearly independent. So part of the game is just translation. What does that mean, linearly independent? Does anyone remember what linearly independent means? John?
Well, there's only the trivial solution is 0.
Okay.
That's the only solution.
Okay, so this is equivalent to saying that 0 can be expressed in only one way. Only one way. Right? There's only one way to get the 0 vector, namely by multiplying all the vectors by 0 and adding them together. Okay? Okay. And then we have some other things that are equivalent to linear independence. But can we get from here, every vector has a unique expression as a linear combination of vi, to here, 0 has a unique expression. 0 can be uniquely expressed. Can we get from here to here? Don't say anything yet, but just think for a minute. Should I let you guys talk to each other? Do you want to talk to each other? Not really. You're not friends. You don't like each other. You're enemies. You guys don't have enemies.
Wait, so we're trying to prove this you're going to
Proving by assuming that that's false. Assuming that not everything is unique.
The span is a collection of all the variations.
Okay, that's
so we know it's your volume expression one way. We know it's like reverse order. Is that what? Okay.
Okay, so what? Right, we know that everybody in the space has a unique expression as a linear combination of vi. We're hoping that 0 can be expressed in only one way, right? Namely as 0 plus 0 plus 0 plus first guy, etc.
So if you assume that not everything has a unique expression, then you could set 2 of the linear combinations equal to each other.
So you're going to start off by assuming that this is false?
Yeah.
Okay, so I mean that would be useful in trying to prove that this is. I think you're going for a proof by contradiction. Right?
Yes.
Okay. So for proof by contradiction, you'd actually want to assume that 0 could be expressed in 2 different ways.
Okay.
Right.
Yeah. So then you would just have 2 equal linear combinations and subtract one from the other, and that would be a non-trivial way of writing 0, which would mean that something is expressible in 2 different ways, in 2 different linear combinations.
Okay. That'll do. It's actually, frankly, it's almost a tautology. It's almost an immediate. In fact, it is an immediate consequence. You say, well, look. You could say, well, look, everybody has a unique expression. In particular, 0 has a unique expression, right? And you know one expression that works, namely. So let me write it down. So we know. When we assume my assumption, every v in the span can be expressed uniquely as a linear combination of the vi. And you say, okay, well, in particular, 0, the 0 vector, we can write as 0v1 plus 0vn. Right? Is an expression. Is such an expression. therefore unique. So what you're saying, Elena, I'm going to hold till we go the opposite, till we go the other way. Okay. It's actually simpler than what you're saying. Okay, great. And remember what we're trying to show here. We're trying to show that 0 has a unique expression. 0 can be expressed in only this way. So this is sort of like the dumb way, the easy way, right? You're trying to show that 0 can be expressed uniquely. Well, you know that everybody can be expressed uniquely. So just look, here's one expression for 0, and this must be the unique expression. Okay. So there's nothing, that's sort of the uninteresting way. The more interesting way is the forward way. Suppose you know that 0 has a unique expression. Right? Suppose that you know that 0 can only be reached as 0 times the first plus 0. 0 can only be reached in the trivial way. Well then, let's see that that forces everybody to be expressible in only one way. And so what Elena is saying is that, well, suppose there are two ways, right? So suppose V in the span has two different expressions. Right? So suppose that V is expressible as Ci Vi, but V is also expressible as Di Vi. Okay. And not all the i's and not all the Ci's are equal to the Di's. Right? Where Ci and Di are not all the same. So suppose you have somebody where, suppose you have two different ways of expressing the same thing. And Elena says, well, let's look at the difference. Then 0 is summation Ci minus Di. Right? Contradiction, right? What's the contradiction? Does everyone see why that's impossible? Why would that lead to a contradiction?
Because we just said Ci and Di. Ci cannot equal Di, but with that Ci equals Di.
Right. So yeah, you can say it that way. You can say, well, look, we know that the only way to get the 0 vector should be that these all are zeros, right? That all these coefficients must be equal to 0. In other words, the Ci must be all equal to the Di. Right? That's a little different from how Elena was phrasing it, but that will do too. That's fair enough. You're saying, well, by linear independence, Ci minus Di must be equal to 0 for all I. Right? Because the only way to get to 0 should be by multiplying everybody by 0 and adding them. Right? But that would mean that Ci equals Di for all I. And that's a contradiction. Because we said that the Ci and the Di are not all the same. Any questions? Any questions? We could have written this in a non-contradiction in a more direct manner. You could say, well, look, So let's write it directly. You say, well, say that V equals summation Ci di, and V equals di. Then 0 is the difference, and that tells us that Ci equals di for all I by linear independence. In other words, any vector has only one expression. Any V in the span has only one expression as a linear combination of the VI. Okay, so you could do it by contradiction. So by contradiction, or you could do it directly. It's the same proof. It's the same proof. It's just you've written it out slightly differently.
Sorry, how do you get from the first step to the second step? How do you know that 0 equals that?
I just subtracted one from the other. So V is this, and V is this.
Yeah.
So suppose that suppose you have one way, you express V as a linear combination. You express V as another linear combination. Subtract one from the other. Then you get 0 equals the difference. Right? So I took the second equation and I subtracted it from the first equation.
Oh, yeah.
Right? On the left I get V minus V. On the
Oh,
right
yeah.
I get this thing. Okay, so I just subtracted. But then you see, by linear independence, 0 has only one way of being expressed, namely the trivial way, which means that all these coefficients, right? Each of these coefficients must be 0. In other words, Ci must equal to di for each one. So which means that these were the same expression. Right?
Mhm.
So if there's for any vector in the space, there's only one way of expressing it as a linear combination. Okay. Any other questions? Okay, so let's do something concrete. So here's an example, checking linear independence. Right, so somebody gives you 3 vectors, 2, 1, -2, 3, 2, -2, 2, 2, 0. And says, are they linearly independent? Are these guys linearly independent? Right? So what's the question, right? The question is, does anyone see that this is something that we've actually done before? That's sort of a bad way of phrasing. But let me read this. So what are we asking? We're asking, is there some way to get the 0 vector from these guys? Is there a non-trivial way to get the 0 vector as a combination? Right. So we're asking, do there exist C1, C2, C3 such that C1 times the first guy plus C2 times the second guy plus C3 times the third guy is 0, 0, 0. Okay. So not all 0. Okay. And now you see what question are we asking? What do we have to do to answer this question? How do we answer this question? Can you find C1, C2? Can you find? Can you find C1, C2, C3 such a, how do you do it? Just solve the equation, right? So you just do Gaussian, you just do Gaussian induction. This is equivalent to asking, right, can you solve this system? Right? Does this have non-trivial, non-zero solutions? Does this thing have non-zero solutions? Okay. Does the homogeneous problem have non-zero solutions? And so what's that equivalent to? That should be kind of familiar, right? That's actually equivalent to what? Invertibility, right?
Yeah.
In other words, is the matrix invertible? Right? Et cetera, et cetera. So it brings us back to that list of equivalent properties. So what we were doing before really actually was related to linear independence. So we have another way of viewing invertibility, right? So in general, right, if you have some matrix A, an n by n matrix, then its columns are linearly independent if and only if A is invertible. And you just go through the same argument as we did right here. We went through the argument concretely, but we could just write this in general using general matrix notation, and then do the same thing. Teresa.
Oh, no.
Okay. Okay. Is everyone all right? All right. Simple. Okay. Observe. There's one observation that. A is invertible if and only if A transpose is. Right? That you know already, because for a multiple, you can argue that in many ways. Somebody tell me why. Why is this true? A is invertible if and only if A transpose is invertible. Give me one reason. Give me one argument. You could have many. for example, you could think about the determinant. Right? You were about to say.
Yeah.
Yeah. The determinant of A transpose is
the determinant of A.
the determinant of A. So if this is non-zero, this is non-zero, if and only if this is this guy's determinant is non-zero. That's probably the easiest way. They've got the same determinant. So invertibility is equivalent to the determinant being non-zero, blah, blah, blah. Okay, so so that tells you, if we go back to the previous fact, right? The columns are linearly independent if and only if well, the columns are independent if and only if the matrix is invertible. The matrix is invertible if and only if the transpose is invertible, which is equivalent to the columns of the transpose being invertible. That is to say, the rows of the original matrix, right? So the rows being linearly independent, this could seem like really mysterious at the beginning, right? The rows are linearly independent if and only if the columns are linearly independent, right, for a square matrix. That could seem like magic at the beginning, but now you see that it's not at all mysterious. Or is it mysterious? You all look sort of mystified. But maybe that's just my perception. Yes, thank you. Yes, thank you.
Are we a particularly mystified class, or is this something that?
Are you a particularly mystified class?
Yeah.
Yes. At least today you are. Yeah. Today you seem to be mystified, but who knows? Okay. I don't care. I'm just going to keep on going ahead.
Let's go.
Yep. Okay, so cool example. The Wronskian. One of my rules of teaching is to not give a damn about the students. Because you can't, in some sense. In the following sense, like if your students are all kind of gloomy and depressed and like angry or whatever, like if the students are very negative, well, you can't let that affect you as a teacher. Right? So in that sense, one should not give a damn about the students. Okay. Maybe I'll share with you some of my other rules. They're equally, I don't know if they're equally humorous. Example, the Wronskian. So linear independence in the functions which are n-1 times continuously differentiable on AB. Okay, so n-1 times continuously differentiable functions. Okay, they have n-1 derivatives, and all of them are continuous. Okay, so here's the definition. Yeah, it's easy to misuse or misunderstand the rule of not giving a damn about your students, so be careful if you become a teacher. Given n functions in Cn-1 AB, we define the Wronskian W of f1 to fn as a new function. So the Wronskian is going to be a function on AB into R. It will also be, these guys are, the fi are all functions from AB into R, the Wronskian is also a function, such a function. And we define it by W blah 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 of x as the determinant of this matrix f1x, f2x, fnx, f1 prime x, f2 prime x, fn prime x, down to the n minus 1th derivative. Fn minus 1, f2 n minus 1th derivative, fn n minus 1th derivative, nx. Okay. So just to give a concrete example, right? If I had something like f1 is, say, x squared plus 1, and f2 is, say, the sine function. Then the Wronskian of these two guys would be the function that gives me the determinant of x3 plus 1, 2x, sine x, cosine x. Right? So it would be x squared minus 1 cosine x minus 2x sine x. So this would be the Wronskian of those two functions. Okay, everyone all right with the definition of the Wronskian? It's pretty simple, right? You just take a bunch of functions, you put them on the first row, and then you take derivatives of them down. Okay, here's the theorem. If there exists a point x in AB where the Wronskian is not equal to 0, then the Fi are linearly independent. So if there exists a single point where the Wronskian is non-zero, then that guarantees that the functions are linearly independent. Okay. Right, so right, if we were looking at this thing on an interval that contains 0, you'd say, well, look, at 0, this thing has the value 1. Right, the Wronskian is 1, and so we know that these functions are linearly independent functions. Okay? You probably knew that from the beginning. You knew that there's no way you could combine these guys to get the 0 function except by multiplying them both by 0. Okay? But this gives you another way of seeing it. Okay. Okay, so this sounds like sort of like a fabulous theorem, but in fact it's quite trivial. If you look at the contrapositive, right, let's consider the contrapositive. Right, that if the Fi are linearly dependent, then what am I going to say? What's a contrapositive? Remember, you have some statement, contrapositive is not A, it implies, not B implies not A, and these two things are logically equal. Yeah, Mia.
The Wronskian has to always equal 0?
Yeah, the Wronskian will be 0 everywhere. And the Wronskian is Okay, right? Because the statement A is there exists a point where the Wronskian is non-zero. The negation of that would be there is no point where the Wronskian is non-zero. Right? There is no point where the Wronskian is non-zero. In other words, the Wronskian is zero everywhere. Okay. So let's look at the contrapositive. We'll prove the contrapositive. So let's assume, let's assume that the Fi are linearly dependent. Why does that force the Wronskian to be zero? So these guys are dependent. I'll let you, this, I think you can do this. So take 2 minutes and see if you can get the answer. Anyone have an idea? Suppose these guys are linearly dependent, right? What does that mean? Linearly dependent means that there's some non-trivial way of getting the zero vector. Or you could say it means that one guy is a linear combination of the other guys. Right? Or
It's not invertible. Therefore, the determinant zero is the Wronskian.
well, that's a little bit. That statement about invertibility is really for vectors, and I mean Euclidean vectors, right? Yeah, it's you remember when we stated that thing about vectors about invertibility. It's really talking about you start off with some matrix, right? You start off with some matrix, right? But here we're talking about functions, so it's not quite the same. Yeah, but let's go backwards to the previous thing. That linearly dependent means that one guy is a combination of the other guys. Right? So, what's the generality? Say, Fn is some combination of the previous guys. So what does that tell you about the Wronskian? Right, remember what the Wronskian is, right? The Wronskian is going to be the determinant of this thing, F1 and F2, Fn, F1, Fn is summation Ci Fi, and I equals 1 to n minus 1. Right? So why does that equal to, why does this determinant equal to 0? Equals 0. And say, Haley,
Would they end up being like the same?
what would be the same?
Is the determinant, I mean, not the determinant, the derivative would
Yeah.
end up being the same, sort of the same down the columns?
Yeah. So
And then the
yeah.
determinant would equal 0 because they're the same.
Basically. So what you see then, this Fn is summation Ci Fi x. Right? The first derivative is going to be Ci Fi prime x. The n minus 1th derivative is going to be Ci Fi n minus 1 x. Right? So they're all the same. They're all the same combinations of the previous entries in their row. Right? So then you just say, I'm going to take the first row, right? Right. If we take, we see that this whole row, this row is a linear combination of the previous rows. I'm sorry, this column is a linear combination of the previous columns, right? And so the determinant is 0. Right? If you have any matrix and you have that one column is a linear combination of the other columns, well then that's going to make the determinant 0. Right?
Sorry, how do we know it's a linear combination of the other columns?
Look at it, right? This one, so F1, F2, Fn, right? Right? You take C1 of the first guy, plus C2 of the second guy, plus C3 of the third guy, blah, blah, blah. You add them together and you get this, right? Use the same coefficients, C1 of the first, C1 times the first guy, blah, blah, blah. You add them together and you get this. Right? In every entry, this entry is a specific linear combination of the previous entries, right? This whole column is C1 times the first row plus C2 times the second row, etc., right? Plus the n minus 1 times the n minus 1, right? So this last column is redundant, right? It's a combination. It's a linear combination of the previous guys, and so if you did like a column reduction on it, then you could get rid of this column. Right? So that tells you that that determinant is going to be 0. Is that clear? I think that's clear. Right? Let me say it this way. If this last column were the same thing as the first column, then the determinant would be 0. Right? Then we have something that's about the same thing. The last column is a combination of the previous columns, so the determinant is 0. That's basically the argument. So the determinant is always equal to 0, right? And so that's the end of the proof. The book gives a slightly different argument. If you're curious, you can read it. Basically, but it's just basically the same thing. Okay. Any questions? My dear mystified students, any questions? Yes, Henry.
Okay.
Yeah, great.
Can you repeat how that column equals 0 again?
It's not the column that equals 0, but the determinant of the whole thing equals 0, because this column is a combination of the previous columns. So like, if I had a matrix 1, 0, 1, 2, 2, 2, and I noticed that this last row was just this row this last column was the sum of the first two.
Yeah,
Then I know that this matrix has a determinant of 0,
okay.
right? Because if you turned it sideways and did row reduction on it, then you could get rid of this guy, right? If you took the transpose and then did row reduction on it, then one of the rows would vanish,
Mhm.
right?
Okay.
So that's all we're saying, right? You can, if a column, if in a matrix some row is a combination of the other guys, well, the determinant is 0.
Yeah.
Similarly, if a column is a combination of the other guys, then the determinant is 0, right?
That makes sense.
How do we know that the Wronskian is, how do we know that works for the Wronskian? Like, how do we know that, that holds true?
Well, so the Wronskian at any point, we're looking at the Wronskian at a particular point, okay? That will give us a matrix of numbers,
Yeah.
okay? So what you're saying is true. You have to think at each point, you get a matrix of numbers where this last column is a linear combination of the previous columns, right? And we see from from our knowledge of matrices of numbers, if one column is a combination of the other guys, then you get 0. Okay. So what we notice is that at each point we get 0, and so the Wronskian is going to be 0. It's going to be 0 every time. Okay. Okay, that's it. See you guys next Monday.